Um, okay, well, should we start, Shalev?
Sure.
Okay, well, welcome everyone to another TCS Plus talk. And we're very fortunate to have Shalev Ben David giving a talk about forecasting algorithms, minimax theorems, and randomized lower bounds. And Shalev is an assistant professor at University of Waterloo, where he's done fantastic work on computational complexity as well as quantum computing. And before we start, let me just mention that next week we'll have another talk by Shuai Zhao, who'll be talking about counting complexity, and also give a shout out to the rest of the organizers, which include Clement Canon and India Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, and Tomas Vidik. And lastly, I'll encourage people to sort of ask questions and feel free to unmute yourself. And yeah, so that's it. So Shalev, please take it away.
Okay, thank you. All right, so I'll be talking about forecasting algorithms, minimax theorems, and randomized lower bounds. And this is joint work with Eric Blake. Okay, so hold on. Okay, so this project sort of started from the following question called the composition question in query complexity. Suppose you have a Boolean function f, which takes in n-bit strings and outputs a 0, 1 value. We let R of f denote the randomized query complexity of f, which is the worst case number of randomized queries to the input required to compute f to bounded error. So here we are reading the bits of the string, and our goal is to compute f of x. So in the composition question, we're given another function g, and we define the blockwise composition of f compose g, which is basically taking n different copies of g and plugging the outputs of g into the inputs of f. This gives us another Boolean function on a larger input string. As shown in the figure, and what we know is the randomized query complexity of f compose g is at most the randomized query complexity of the complexity of f times the randomized query complexity of g, up to a log factor. And you can see this sort of by imagining running an algorithm. This algorithm wants to query a bit of the input to f, then you run the algorithm for g as a subroutine there for that bit. And you need a log factor from amplification, but otherwise this is strategy. So is it true that the randomized query complexity of f compose g is at least the randomized query complexity of f times the randomized query complexity of g?
So Shalev, there's in the chat, it seems some people are having a hard time hearing you. I don't know how to fix it, but perhaps would using the mic in the computer be better than the headphones?
I can try, yeah. Can you hear me better like this? Or actually, where can I see the chat? Okay, hold on. Let me. Okay.
Yeah, it seems it may be better now.
Okay, I'll try to keep going. Sorry about that. Okay. Right. So as I was saying, the composition question in query complexity simply asks whether this sort of naive approach to computing F composed G is the best possible for randomized algorithms, or in other words, is the randomized query complexity of F composed G at most the randomized, or at least rather, the randomized query complexity of F times the randomized query complexity of G. I sometimes get the following line of questioning when I tell people about this work. I have people asking me, sort of, why do you study query complexity? Query complexity is not real life. It's sort of like just a very simple toy model. And I usually answer, well, at least we can prove things. Sort of in usual computational complexity. So in usual computational complexity, it's very hard to prove lower bounds. We don't know how to prove the non-existence of algorithms. Of course, in query complexity, proving lower bounds for specific Boolean functions is usually pretty straightforward. We say in query complexity we might prove the non-existence of 3 different algorithms in the shower each morning. Okay, so that's usually my response, but the colleagues will come back to me and say, okay, but who cares if you can prove things? It's still not real life. Okay, it's kind of an uncomfortable line of questioning. But you can at least say query complexity is at least a useful model for real life. By studying query complexity, we hope to gain some insights about algorithms as they work in practice. So this is not only a mathematical kind of toy problem, but maybe it will also teach us something about how algorithms really work. But then the colleagues reply, all right, maybe this is true for some more complicated complexity measures like quantum algorithms or the polynomial hierarchy. But when is the last time that randomized query complexity gave us new insights about randomized algorithms? Don't we already understand randomized algorithms pretty well? And so sort of for this talk and for this work, I want to highlight first the insights we gained from studying this problem that generalize beyond query complexity. And really, I claim teach us something new about randomized algorithms that we didn't know before. And the main insight that I think we got from this work is the following. Suppose you are dealing with randomized algorithms in the small bias regime. So by that, I mean the bias will be 1 over polynomial in the runtime rather than, say, 1 over exponential in the runtime, which would be more similar to a PP style regime. And you want to do a fine-grained analysis, meaning you care about polynomial factors, both in the runtime and in the bias. Then the insight is consider switching from talking about the bias of the best random algorithm to talking about the score of the best using a proper scoring rule. This type of setting, you sometimes see it, for example, in cryptography, where people talk about small bias randomized algorithms. But of course, in cryptography, usually you don't care to do a fine-grained analysis. So here, the setting is sort of one in which we do think about biases that are say 1 over poly n, but we want to care about that polynomial factor. Okay, so to explain this insight, let me start by talking a bit about scoring rules. So here's the intuition for scoring rules. the setting is sort of this. Suppose you're paying someone to make a prediction. How should we reward them? So suppose they tell you something like this, 62% chance of rain tomorrow, or 89% chance of that Biden wins. I assume you all came to this talk to kind of get a distraction, avoid the election. So yeah, sorry about that. It's not that easy. Okay, but anyway, somebody gives you a prediction like this. Then what happens? I mean, either the prediction comes true or not, presumably. You could reward them if they are right. But doing so does not distinguish a prediction that says 100% from a prediction that that merely says 51%. You could give the first guy 62% of the reward if it rains, for example, and kind of proportional to the prediction. But actually, if you think about it, this gives exactly the wrong incentive. So incentivizing it actually incentivizes both to just say 100%, even if they believe there's truly only a 51% chance. So more generally, you can say, okay, suppose the prediction is P, then what should the reward be if the event happens, and what should the reward be if the event does not happen? And a scoring rule is basically the name that we give to any reward function like this. So it's any function that takes probabilities and outputs real numbers. And usually we think of giving the reward S of P if the event happens that was predicted with probability P, and S of 1 minus P if the event does not happen. Okay, so we say that a scoring rule is proper if it solves the question from 2 slides ago, if it incentivizes a Bayesian predictor to give her true subjective probability. So what does that mean? It means suppose the predictor Alice believes that the true chance of rain is P, and she outputs prediction Q. So she might lie about what she really believes. So what does she expect her reward to be? So she expects with probability P chance, she gets reward S of P. And with probability 1 minus P chance, she gets reward S of 1 minus Q, because that's the situation in which the event does not happen, and she's rewarded with S1 as her prediction. We want the property that this equation as a function of Q is uniquely maximized at Q. So we want Alice's incentives to be that she should say 62% if she believes in 62% of the rain. So a scoring rule that S is proper if for every probability P that represents Alice's true belief, the expression P times S of Q plus 1 minus S of 1 minus Q as a function of Q has a unique maximum at Q equals P. Okay, so what's an example of a proper scoring rule? One simple example is just taking the log of the forecast of the prediction. This is sort of the amount of surprisal in information theory. So we would pay Alice log of, Alice pays log of 1 over 0.62 if she predicts 62% chance of rain and it rains. And she pays log of 1 over, minus 1 minus this if her prediction fails. And this turns out to incentivize her to give the true estimate. It's not hard to check just by basically, going to the equation in the previous slides and just taking derivatives, basically. So for these two guys who are giving us predictions, with this scoring rule, then the score, taking the logs of the probability, then the first guy sort of knows that his reward will be either negative 0.48 or negative 0.97. The second guy knows that here's the reward will be either 0.12 or negative 2.21. So, and the point is that these hopefully, given this knowledge, that they would probabilities that maximize their expected score, which would be their true probabilities if they're Bayesian. So, of course, these are negative. So this means that they pay us no matter what happens. We can imagine a situation where we want to pay them. So in other words, we want S of Q to be positive. So of course, we can always scale S of Q to be, by scaling by positive constant and adding a constant. And you can try to make it constant, to make the scoring rule positive. But of course, it doesn't work with the log scoring rule, because for the log scoring rule, log of 0 is negative infinity. So there's no amount of shifting this function that will give you something positive. But there's other scoring rules. One famous one is the Brier score. The Brier score is this quadratic score, basically. It's negative of 1 minus q squared. It's also proper. And this one, you can actually shift it to make it bounded, for example, by adding 1. And it will be bounded in 0, 1. And this one really was proposed originally in 1950, really for the task of incentivizing weather prediction. So, you want to pay your weathermen in order to incentivize them to give a correct prediction, or at least a prediction they believe in. Turns out there's many other scoring rules. So this kind of surprised me when I first encountered this, but almost every function you pick out of the hat turns out to be a proper scoring rule, except for the couple illustrated at the beginning that weren't, just having the reward be proportional to q, for example. But there really are a surprising number of these functions. There's a whole entire families of them. So for our work, we're interested in a very specific one. It's this one, S of q equals 1 minus square root of 1 minus q over q. And we've normalized this already so that S of 1 equals 1, S of a half equals 0, and S of 0 is negative infinity. This means a correct prediction with perfect confidence gives you 1 point. A 50-50 guess gives you 0 points. And an incorrect prediction with perfect confidence loses infinity points. As you can see, this scoring rule is not bounded. This here. This scoring rule is not bounded. It's also more obscure. The previous ones had mentions in the Wikipedia article, for example. We did eventually find it in the literature under the name boosting loss, which is kind of suggestive. It has the property of being amplifiable, and we'll talk about this. But this is a property that's crucial for our purposes. So in order to talk about that, let me just talk about forecasting algorithms. These are algorithms that basically act as predictors. So these are going to be randomized algorithms that output a confidence in 0, 1 instead of outputting just 0 or just 1. So instead of a Boolean output, they give a real number output. And intuitively, what this real number should represent is the confidence the algorithm has that the answer is 1 on this input. Okay. And we define the score of a forecasting algorithm to be the worst case expected score. So this is going to be the worst case over inputs of the expectation over the internal randomness of the score with respect to the right answer. So of course, the score for a prediction depends on whether the prediction came true. So whether the prediction came true here, we will evaluate based on whether on the value of f of x, on the value of the function that the algorithm is trying to compute. Okay, and note that when we do the definition this way, there's no longer any interpretation of the form incentivize a Bayesian agent. That's because the only source of randomness here is the internal randomness of the algorithm. In particular, belief anymore. When your inputs are worst case, it doesn't make sense to say, oh, you're a Bayesian agent and you have this much belief about the input being this or that. No, the input is worst case, right? So there's no prior. No prior, therefore, no posterior, no definition of properness anymore effectively. I mean, of course, the scoring rule itself might be proper, but it no longer tells us that the algorithm is some Bayesian agent whom we're trying to keep honest. But still, the setup is well defined. We can still evaluate a randomized algorithm using scoring rules in this manner and just see what happens. And here's why you might want to do this. So here's a kind of motivating example for where this could, how this could possibly behave differently from a regular randomized algorithm. So consider the following two tasks in query complexity. One task is, in both cases, you're going to get inputs, Boolean strings as inputs. In one task, the goal is to distinguish Hamming levels n minus root n over 2 and n plus root n over 2. So for example, these two input strings come from the two different Hamming levels. In the other task, your goal is to distinguish the Hamming levels 0 and root n. So you're trying to distinguish these two types of strings. In terms of a picture, if this is kind of the Hamming weight diagram. So at the top will be the all one string, at the bottom is the all zero string. So on the left, we've promised out this root n section in the middle of the Hamming weight, and on the right, we've promised out a root n section right above the all zero string. Okay, and you want to distinguish, in both cases, you want to distinguish the top from the bottom. And you get to make queries to the input string, so you get to kind of look at a certain number of bits. In this case, the budget is going to be one query, so you get to look at exactly one bit of the input. Okay, so you get to pick a bit of the input, only look at that one bit, only see a single 0 or 1, and your goal is to distinguish these two Hamming layers. Now, it's kind of not too hard to see that on the left, the best possible bias you can get is 1 over root n. In other words, if you only see a single bit, that's 0, 0, 1, then you cannot, your success at this task, your bias, which is the probability of success minus probability of error, will not be better than roughly 1 over root n. And the best possible score, according to this proper scoring rule, turns out to be even worse. It's 1 over n on the right. But on the left, you can see that the best possible bias is still 1 over root n. You still have just a root n gap. So if you only pick a single bit from the input string, your chances of this bit being used to detect a difference between these Hamming layers is still 1 over root n. So the probability of success minus probability of error for any randomized algorithm here must be at most 1 over root n. However, the best possible score is also 1 over root n. So look at what happened here. When evaluated according to the bias, these two problems looked the same in terms of difficulty. The problem on the left looked as hard as the problem on the right. They both with one query, the best possible bias was 1 over root n. But when you evaluate according to these forecasting algorithms and their scores, and you ask what is the best possible score of a forecasting randomized algorithm, now the two problems look very different in difficulty, and the one on the left looks harder. So distinguishing two Hamming layers near the middle seems harder now than near the edge, near the all zero string. And one interesting property here is that this actually matches the sort of amplification behavior of these properties. So you can ask, now let's increase the budget from one query to more queries. And let's ask, okay, just how many queries do you need to make before you can solve this problem to bounded error? So And let's suppose you're just really amplifying your algorithm. So you're repeating this one query algorithm a certain number of times, let's say k times. And you just want to pick k so that after seeing this many queries, you can fully solve the function to bounded error. And it turns out that on the left, you would need to repeat n times. So you need to really query n bits before you can solve this gap hamming problem to bounded error. But on the right, you only need to repeat root n times. So the problem, these two problems really are different in difficulty. But when you only budget one query and try to ask which one, where can you achieve more bias, that setting does not reveal this difference in difficulties. So it doesn't reveal the fact that the problem on the left will be harder to later amplify than the problem on the right. On the other hand, evaluating these algorithms with a proper scoring rule does reveal this. So when you evaluate these algorithms with a proper scoring rule, you kind of suddenly see that the problem on the left really is harder. The best possible score you can achieve with one query is 1 over n. Okay, and this is, it's sort of because, you know, for a forecasting algorithm, when you run it on the right, you know, it gets to tell you that it's now certain of the answer. So it gets to tell you, oh, I found a 1 in the string. So now I'm certain that this is a 1 input. So it gets to express this with its confidence. Whereas, you know, and on the left, it might express very weak confidence in the answer. But a regular algorithm that only outputs a prediction 0 or 1 instead of probabilistic prediction, it doesn't have any room to express uncertainty. It can't say, oh, this time I'm certain, this time I'm not certain. And for this reason, you know, it's the intuition here sort of is that the scoring rule gave you a more fine-grained analysis of the success of the randomized algorithm. The bias was missing something. And it turns out forecasting algorithms can be amplified. So when using this one special proper scoring rule, this one, and when you evaluate an algorithm according to the worst case expected score, then you can sort of do the following. So suppose on a fixed input x, you run your forecasting algorithm several times, and it gives you different predictions. It gives you different probabilities for what it thinks the value of f of x is, like 0.6, 0.9, 0.8. So it turns out you can then combine these outputs in order to get a single prediction that summarizes them. And what's the natural thing to do here? Well, if you're Bayesian, the natural thing to do would be to convert probabilities to odds ratios. So this is basically saying 1 minus 0.6 over 2, the ratio of by all the odds ratios. And again, Squirrel expects new algorithm, one that combines k prediction, 1 minus s to the k, where k is the number of repetitions and s is the expected score of r on x. Okay, so by combining the predictions in this way, you can be certain that you will increase the expected score of your algorithm. This is not true how application works for randomized algorithms, except that is nicer. It's first of all, it's kind of it's linear. This expression is roughly s times k, but also you have an exact expression for the new score. Whereas if you just repeat a randomized algorithms a few times, don't have a nice closed formed expression for the new bias of your algorithm. Another property of these scoring rules is that you can convert between scores and biases and vice versa. So if you have an algorithm that you know achieves bias gamma, you can convert it to a forecasting algorithm with expected score at least gamma squared over 2. And this you can do just by running your algorithm. It gives you an answer either 0 or 1, and you just you just attach to it the confidence that bias gamma implies. So the algorithm output gave the output 1, and you instead say 1 minus gamma over 2 if the algorithm outputs 0. And this turns out to give you the guarantee of expected score at least gamma squared over 2. You can also go backwards. So if you have a forecasting algorithm with expected score S, and you want to convert it to a regular algorithm with bias at least S, you can run your algorithm. It's going to return some prediction Q, that's a real number in 0, 1. And then you can sample from Bernoulli Q. So you will say 1 with probability Q and 0 with probability 1 minus Q. And this will turn out to have the guarantee that if your original expected score was at least S, then your bias for this algorithm is now also at least S. Both of these hold just with respect to that one magic scoring rule. They don't hold for all scoring rules. And this means that the best achievable bias is within a quadratic factor of the best achievable score, pretty much in any model of computation, because these transformations only apply to the outputs at the end of the algorithm. And in particular, if you care about constant error, then constant error is the same as constant expected score up to constant factors. So really, this is just saying score is the same as the bias up to a quadratic factor, but it's a more fine-grained way of measuring success. It's sort of what bias wanted to be. Okay, at least with this one scoring rule. That's the intuition we've gotten from this work. Why is it more fine-grained? Again, it's basically because it's allowed to say I'm certain in this case, or I have no idea in this case. And a normal algorithm is not allowed to tell you this. It's not allowed to express this to you. And so it's kind of limited in how much it can succeed. So again, the main insight is, this is a repeat of before, if you're dealing with randomized algorithms in this small bias regime, and you want to do a fine-grained analysis, meaning you care about polynomial factors, consider switching from talking about the bias of the best randomized algorithm to talking about the score of the best forecasting algorithm under a proper scoring rule. Okay, and that's sort of part 1 of the talk. Okay, I guess, I don't know if people want to ask.
Could I ask a quick question?
Yeah.
I was wondering if you could share some insights about the role of that specific score in these results.
Yeah, so right. So I mean, the properties we wanted from the scoring rule. The first property was that it's amplifiable. So this is kind of a strange property to ask because it only applies to these worst case setting and not to the kind of Bayesian setting where you had a prior, and that's kind of where most of these scoring rules naturally live in. So we wanted this amplifiability property. And the second property we need is that score is polynomially related to the bias, in this case, quadratically. And both of these properties we don't know how to show for any other scoring rule. So, you know, it's kind of interesting that the one scoring rule happened to satisfy both. One property we didn't really need in the end is actually we didn't really need the property that it was proper. So this is a scoring rule. We didn't actually use the fact that it incentivizes a Bayesian agent to give her true subjective probability, although this is true for the scoring rule. It is proper. And kind of one thing you might notice about, let me just see. Hold on. Yeah. So if you look at the definition of the square rule here in the middle of the slide, one distance. So if you're familiar with Hellinger distance between two distributions, you might kind of see a similarity here, and this turns out to be a real connection. In particular, like the connection with Hellinger distance comes in the setting where you want to distinguish two distributions. You want to say, okay, I have two distributions, D0, D1, let's say, and I'm giving a sample from one of them, and I don't know from which, from either D0 or D1, and my goal is to predict which one. This is kind of a standard problem in statistics. And now if you ask, okay, what is the best success probability I can have? What is the best bias effectively for this task? And then the answer is the total variation distance between the two distributions. But you can ask instead, what is the best possible expected score for this task? So basically now you get to say whether it came from D0 or D1 and attach a confidence, and you'll be evaluated by the scoring rule. What is the best possible expected score? So for this one scoring rule, the best possible expected score will be the squared Hellinger distance between D0 and D1. So this one scoring rule is sort of like a pointwise representation of squared Hellinger in a way that's analogous to how bias is a bit like the pointwise representation of total variation distance. And that's maybe also where the amplifiability comes from, because the Hellinger distance behaves nicely under tensor products or direct products of distributions. So maybe this sort of explains, and also we know that, of course, the Hellinger distance is quadratically related to total variation distance. So maybe sort of all of these properties kind of come from this connection.
Great, okay. Thank you.
Yeah. Right. So the second part of the talk, I wanted to talk a little bit about Minimax theorems. And one of the papers we got from this work is a new Minimax theorem for randomized algorithms, which I want to explain a little bit. So to start with, Yao's Minimax, if you recall, it's the statement that applies to what I call concrete computational models, basically models in which the input set is finite. This is kind of one of the key properties you need for Yao's Minimax to apply. And it says basically this. It says, for any function f you wish to compute, there's a hard distribution mu over the inputs, such that computing f against mu is as hard as computing f in the worst case. Okay, it gives you a hard distribution such that even if you knew the inputs come from the distribution, you still can't solve f any better than before. It's very useful for lower bounds because this, especially when you combine different functions like in composition, you get to always assume there's a hard distribution that certifies that f is difficult. In fact, you can read it as a tight lower bound technique because you kind of guarantee that this certificate of difficultness, the difficulty that comes from the distribution, can always match the real hardness of f to worst case error. Right. So I mean, meaning Yao's Minimax gives you a distribution against which all deterministic or even randomized algorithms fail if they don't use enough cost. If they don't, if they don't sort of work as hard as you need to work in the worst case. And here we want to give a generalization of Yao's Minimax. Yao's Minimax, well, it's already pretty general. It also works for small bias algorithms. And for small bias algorithms, it will say something like this. It will say, let T be the worst case cost of computing F to bias gamma. Then there's a hard distribution mu such that any algorithm achieving bias mu against inputs, bias gamma rather, against inputs from mu must have cost at least T. Okay. So again, it's as hard against to compute the function against mu as it is in the worst case. However, this is one problem with Yao's Minimax is that the distribution mu depends on gamma. You don't just get a hard distribution that works for all bias levels. You get a hard distribution tailored to your one bias level. And for different bias levels, you will get different hard distributions. And also, just in general, there are basically no guarantees on the distribution except that it's hard. So in particular, this hard distribution might not put even weights on the 0 inputs and the 1 inputs, although that might sound ridiculous. You know, it might put 60% weight on the 0 inputs, 40% weight on the 1 inputs. That's still hard. That could potentially still be hard to compute to error 1/3. So you don't really, you have to kind of later work to start with the distribution mu and try to impose whatever conditions you wanted on it. It might also just, so in particular, mu might be trivial to solve to a bias smaller than gamma. So it certifies hardness to bias gamma, but what about bias, you know, gamma over 2? And maybe it's just totally trivial. In fact, maybe you don't need to look at the input because mu is not balanced on 0 and 1 inputs. So this is the question we were asking. Is there a distribution that certifies hardness of the hardness of F against all bias levels at once? Can you kind of do Yau's minimax, but uniform across the bias levels? So in other words, you might ask this: is it true that for all F, there exists a distribution mu, a hard distribution mu, such that for all bias levels, then this R subscript gamma superscript mu, this is the cost on average against distribution mu of computing F to bias gamma, is at least R sub gamma of F. This will denote the worst case costs of computing F to bias gamma. But note that the quantifiers are exchanged compared to the regular Yau's minimax. So we want here exists mu such as for all bias levels this holds. Unfortunately, this statement actually turns out to just be false. It's not too hard to show in pretty much any model that interests you that this just won't be true. Instead, we make the following statement. We ask, is it true that for all functions F, there exists a hard distribution mu, such that for all bias levels gamma? It's the same thing on the left, but we replace the right-hand side with gamma squared times R of F. And gamma squared times R of F, the gamma squared, the right-hand side here is smaller than the one above because of amplification, because you can always amplify a randomized algorithm with bias gamma to one with constant bias. By the way, here I'm using R of F with no gamma to denote the constant error regime, the constant error cost of computing F. So you can always amplify an algorithm that achieves bias gamma in the worst case to one that achieves constant bias or constant error in the worst case. And this will cost you 1 over gamma squared. And for this reason, it's not hard to check that gamma squared times R of F is smaller than or equal to R sub gamma of F. So this statement is weaker, but it has the property of being true, which is always desirable. And this is what we show in our work. So to just briefly, in the remaining couple of minutes, sketch how we do this. So first, how do you prove Yau's minimax? Well, the way you prove it is you view randomized algorithms as probability distributions over deterministic ones. So if you denote by A the set of all deterministic algorithms, then P will be the set of all probability distributions over A, or the convex hull. And similarly, you have a set of inputs, and you use notation, let's say delta, for the set of probability distributions over the inputs. And then Yau's minimax can basically be written like this. It can basically be written as a true min-max theorem. In other words, a min-max equals max of min of some function, where the function basically represents the error that the algorithm makes on that distribution. And to kind of see why this statement is the same as the one before for Yau's minimax, you note that the inner function is bilinear. So it's linear in R and linear in mu. And then this means that the inner min and max are both achieved at a boundary point of the convex hull. which basically means that you can replace the max over mu with a max over x on the left and the max over r with a max over d on the right, the min rather, over d over on the right. And when you do this, then you can sort of get the interpretation that there is a hard distribution, which is given by the right-hand side, against which, average case hardness, which is the expression on the right-hand side, is as hard as worst case hardness, which is the expression on the. Okay, so this is how you prove you has minimax. You just need this min of max theorem. Min of max equals max of min for bilinear functions. So to generalize, you can note that, well, what the Diaz minimax theorem uses, it uses something called von Neumann's minimax. It's also a special case of LP duality, but it's also a special case separately of something called Sion's minimax. And Sion's minimax gives you this inf sup theorem for function alpha. Of course, there's requirements on alpha, but alpha, instead of being bilinear, it's only required to be what's called semi-continuous and quasi-saddle. Okay, so I guess maybe we don't care exactly the details of what this means. There's some continuity condition and some kind of convexity concavity in the arguments condition. Moreover, one of the two sets, the own which you're maximizing, has to be compact, but not both necessarily. In our case, we have finite input sets, so that's easy. The distributions over those inputs will always be compact. And so what we notice in this work is that using Sion's minimax, you can show the get a min-max theorem for a ratio of linear functions. So here, cost and score are arbitrary bilinear functions, and then that plus superscript denotes the max of 0 in the function. And also, we interpret division by 0 to give infinity. So in other words, it's just a general minimax for the ratio of bilinear functions, and it follows from Sion's minimax. And it even works if they're what's called saddle functions, which is a generalization of bilinearity. So just very quickly to wrap up the proof. So you could do the following. You could, right? Okay. Why don't we interpret the cost and score in this theorem as being the cost of a randomized algorithm and the bias of a randomized algorithm? Then you get a valid minimax theorem of this form. However, we don't get the interpretation we wanted. Neither side here is equal to the worst case complexity of computing the function. So we get a theorem, but it's not very interpretable. And part of the problem is that we would like the left-hand side to look like cost divided by bias squared. Why? Basically because amplification costs 1 over bias squared. So if the left-hand side said cost over bias squared, then by amplification you could show it's just equal to the worst case cost of computing F2 bounded error. It will be exactly equal up to constant factors, I guess, that come from the amplification. So that would be really nice if we can put a divide by bias squared on the left. Unfortunately, we can't just put score equals bias squared in our theorem because the bias squared is not bilinear and it's not saddle and it doesn't satisfy the properties. So that minimax theorem will in general fail. So instead, we, I guess as the notation suggested, we are going to use the squaring rule. And this helps because the worst case expected score can actually be amplified linearly. That is, this amplification expression, 1 minus s to the k, is roughly k times s, which is linear. So to get from s, which might be small, to a constant, you only choose k to be 1 over s. And therefore, cost of an algorithm divided by score. Now on the left-hand side, you will be able to kind of use amplification to argue it's equal to the worst case cost of computing f. So the left-hand side becomes r of f by amplification. And the right-hand side now tells us that there exists a distribution mu such that for any score target S, the cost of achieving score S against mu is at least S times R of F. And then you can use the fact that scores and biases are quadratically related to get the lower bound of gamma squared times R of F, which is what we wanted. And this turns out to work in pretty much any model of computation we tried, as long as both Thia's minimax and amplification work. So this is randomized query complexity. We have a theorem there. Randomized communication complexity. Circuit models. We have a version of Pagliaso's hard lemma that's uniform in this query and communication, polynomial degree and approximate log rank. So you can kind of check the paper for precise versions of the minimax statement in each of these models, if you care about one particular one. Well, just okay, very briefly, I'll just put on the slide here, but basically, if you have in query complexity or communication complexity, you can define what's called the transcript of an algorithm, which is basically everything it looked at. And you can interpret our minimax as saying the following as well, which is that if your algorithm achieved squared Hellinger distance at least epsilon between its transcript on the 0 inputs and its transcript on the 1 inputs for distribution, for fixed distribution mu 0 and mu1, then it must have made at least epsilon times R of F expected queries. So you can sort of switch from the bias or score interpretation to our Hellinger distance between transcripts interpretation, where the two different transcript distributions are the transcript of the algorithm on 0 inputs and the transcript of the algorithm on 1 inputs. So this is a useful property. And so finally, this was our query problem originally. We were asking, does the lower bound of R of F composed G is at least R of F times R of G hold? And what we get is effectively, we managed to prove a tight composition theorem. So we managed to show that R of F composed G is at least a measure we called noisy R of F times R of G. We also gave a characterization of noisy R of F in terms of measures we're used to. And we show it's the strongest possible composition of its type. So this means that you cannot replace noisy R of F with any measure that's ever larger than it. And we also show that actually the original composition conjecture is false. So we show that for some F and G, R of F composed G can actually be smaller than R of F times R of G. So it's also kind of telling you that this noisy R of F measure, although it looks annoying, is sort of necessary to put there. Okay, and finally, open problems. Mostly the main open problem is what are some other applications of forecasting algorithms? Also, what about other score rules? We only kind of used one, but can you get any new insights from evaluating algorithms using one of the other ones? You know, what are other applications of the minimax? We showed composition in query complexity using this minimax. Maybe we can do something in other models of computation. Thanks. All right.
So maybe if people have any questions, now is a great time to ask. And if not, I can take us off the recording so we can just chat.